determine whether the series n equals 1 to infinity cosine of n over n squared is convergent or divergent. So notice this question doesn't say anything about absolute convergence anymore. All right, I just want to know if it converges or diverges.
Yeah. First one, we didn't actually have to go back and do the AST.
No, because we did it in the notes before, I think. Yeah, but I just did it again for you.
But like, because we had it absolutely converged, so it was automatically converged.
Oh, yes.
Yeah.
Yep.
We used that to show that.
Yeah, yeah. So if I asked if that series converged, yeah, you wouldn't have to do the alternating series test. You could just show that it was absolutely convergent. You're right. All right, so let's say we're not talking about absolute convergence right now, just convergent or divergent. So you run through your tests, right? I don't want to do the integral test. That's going to be really messy to integrate that, I think. What else do I have? I have comparison tests, but my series has to have positive terms. So you're going to have to write this out, some of these terms here. And so forth. And you're going to see that it's not alternating, and there's actually no pattern to the signs. Some of the terms will be positive and some of them will be negative, but there's no pattern to which ones are positive and negative. So we can't use the alternating series test because it's not alternating series. Okay? We've kind of run out of tests. I said integral test, I didn't want to do. Comparison test, we can't use because they're negative terms. It's not alternating. You could do the divergence test, but I can't compute that limit with the cosine in it. So we're going to use this fact that if I can show that this is absolutely convergent, I know that it also converges. Okay? So let's consider this series here where I take the absolute value. And again, the way the absolute value works, I split it up into the absolute value of the numerator, the absolute value of the denominator, but the denominator is positive, so I can just forget about the absolute value in the denominator. What's nice about having this absolute convergence is you're forcing your series to have positive terms. What test can you use when you have positive terms? Comparison tests. So you're opening up the use of comparison tests, which we couldn't use before. Okay? So let's think about our terms here. This would be, if we're doing a comparison test, this would be our AN. And I've got to create a new series to compare it to. So the series I'm going to compare this one with is going to be 1 over n squared, because the largest that cosine of n can be, the absolute value is 1. Right? So we know that, let me write this down. Cosine of n, it's some value between -1 and 1. So when I take the absolute value, I'm getting a number between 0 and 1. Well, then I can now compare, this one is my Bn. I can now write down the relationship between these two terms, cosine of n, absolute value over n squared. This is less than or equal to 1 over n squared. So this says A sub n is less than or equal to B sub n. And now let's look at the series with Bn in it. 1 over n squared. It's a p series. What's my p-value? 2. So does it converge or diverge? Okay, so I'm going to write that over here. This is a p series. P is 2. P is bigger than 1, so I know it converges. So we can get away with just using the direct comparison test here. My Bn converges, and it's the larger one in the inequality. So the smaller one, An, has to converge as well. Okay? So what we just found out is that this series, cosine n over n squared, converges by direct comparison test. So when I took absolute values, it converged, means my original one is absolutely convergent, yep. So I can now say that this one, which was cosine of n over n squared, is absolutely convergent. Okay. And that theorem I just wrote down said anytime you have something that's absolutely convergent, it also converges. Okay? So this thing also converges. So that's my answer, convergence. This is really helpful whenever your series doesn't have positive terms, because if it had positive terms, absolute convergence and convergence are really the same question. But here, I wrote out some of the terms in my series, and it had negative terms. You have to use a calculator to verify cosine of 1, cosine of 2. Those are going to be positive and negative, and there's no pattern to their signs. Some of them are positive and some of them are negative. It's not alternating. And so for this one, this is really the only way I think that you can show that it's convergent, at least with what we have so far.